Okay, so good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. Today we have Professor Devis Tuia from the Swiss Fédérale Institute for Technology in Lausanne. And with us on the panel, you see also Dr. Lorraine Janté. I'm not sure, Lorraine, that I pronounce your surname correctly. Yeah. And Lorraine has just joined the African Institute for Mathematical Sciences in Cape Town, and she's working as a postdoc in the group of Emmanuel Dufork that you also see on the panel, and that some of you might have already met in the same colloquium not so long ago. Yeah, I will ask now Lorraine, because she's working in the area of Professor Tuia, to please introduce the speaker. So Lorraine, your job.
Yeah, thank you, Francisco. So it's a real pleasure to join this community. So thank you very much, NITheCS, for this great opportunity. And this great opportunity is all the more important that today I have the pleasure of introducing Dr. Devis Tuia, who is going to talk to us about a subject that is particularly close to my heart and certainly close to your heart. And this is machine learning supporting ecology, supporting machine learning. Welcome to you, Dr. Tuia. And if I have to summarize your impressive career path, I would say that you are currently professor at Ecole Polytechnique Fédérale de Lausanne in Switzerland, where you lead the computational science and health observation laboratory. You completed your PhD at the University of Lausanne, where you studied kernel method for hyperspectral satellite data. Then you traveled the world to perform different postdocs. And in 2017, you was chair of the Geoinformation Science and Remote Sensing Laboratory at Wageningen University in the Netherlands. And in 2020, you are back at Ecole Polytechnique Fédérale de Lausanne to study the Earth from above with machine learning. So today you are going to tell us more about how machine learning can help us to study the animal ecology. So yeah, I let you explain more about it.
Thank you very much, Lauren. Can you hear me?
Yes, David, we can hear you clearly, and you're welcome to share your screen if you want.
Very good. So I'll share my screen. There we go. Can you see it full screen?
Yes, now. Yeah.
Fantastic. All right. So good afternoon, everybody. It's good to be participating to this seminar at the NITheCS, if I pronounce it correctly, and which, if I understand well, it's located in Durban, right? Francesco is Durban.
No, it's also located in Durban, but we are a little bit of a delocalized institute. We are based in Stellenbosch, in Johannesburg, and in Durban at the moment. Yeah.
Okay. Wow. So completely decentralized institute. I like that. Okay, so I will skip my joke about telling a plane to Durban many years ago, because I don't know where you guys are sitting, but it was very fun. And yeah, let's get started with the talk then. So yeah, I wanted to give you a tour about the recent research effort we had with in our head, this idea of deploying machine learning technology that is fit to ecological problems in order to facilitate a number of tasks which are often related to animal counting and sensing, and with an idea to help out people who are active in the conservation area, and that could use a lot all this technology. So the idea is that biodiversity crisis, it's something that is really ahead of us. I mean, probably in South Africa you are experiencing it before us, but it's a kind of a well-known fact that there is a high number of species that is at risk of extinction, and that this is not going much better. So there are just this forecasts that were quantifying almost 1/3 of species to be extinct by 2050, and it's something that we should really be worried about. Also because our very recent studies here by Ceballos and colleagues pointed out that if we could be on the green path here, that you can see, I hope you can see my mouse, that if we were on this black line and we could stay on the green by having like massive conservation actions, we are probably going down the gray slope for the time being, which is the business as usual. And we should at least try to go on the orange one by increased conservation efforts. And why this is important? Well, basically because we have been suffering quite a lot by COVID-19 in the last years. There is this climate change specter just ahead of us, and everything leads to think that the biodiversity collapse will be much, much worse because we depend a lot on this biodiversity. So biodiversity helps us be better. It's a strong influence on our health. Species, plants and animals are there. They help us to craft new medicines that are important. They help us fighting against pests, and by everything they do for purificating soils from pollutants, for example, they help us having food. Or imagine the bees that are basically making that we have fruits and things like that. So basically having an healthy biodiverse world, it's in everyone's interest because it will basically help us keep having something to eat, shelter, and be protected by illnesses. So the story is that at this point of the talk, I hope you're not thinking, hey, but this was a talk about machine learning. Why is Devis telling us about all this, about the biodiversity and all the bad things that will happen to us if we don't do things right? But actually, we can take machine learning as a means to help people who are basically making the hard effort to preserve biodiversity in the field. So I have here two pictures, two examples that are people we work with on an almost daily basis. And these are rangers, for example, here in Kolpejeta in Kenya, who are basically patrolling reserves to protect the rhinos and fight against the poachers, or private reserves like the Kuzikus one, that I will talk a lot about it in this talk, where they are basically trying to model the animal populations and needs of grazing, and then how much food is available for the animals. And all this is like a closed loop where by estimating the one, it helps us estimating the other. And if you think that these are very simple problem, I mean, don't get me wrong, but they are not. Because even though it will seem easy to any of us to like count animals in an aerial image, you need to imagine that in this reserve, people do everything by hand. So they, for example, they rent an helicopter, start flying over the reserve and look out of the window and try to count how many animals they have. And they cannot cover much ground, so data samples tend to be pretty small. And even when it goes through like more, let's say, advanced types of censuses, imagine camera trap networks, for example, well, people who are in charge to basically process the information end up being very much behind because they need to go through thousands and thousands, if not millions of images. And very often there are just not the means to efficiently go through all the footage and be ready for the next campaign. So with these two examples, you can see that we can do a lot with machine learning to basically speed up this type of research. So I will just talk about these two things. So the first is that the people tend to do everything by hand. So by doing smarter data collection, we can probably help covering more ground in national reserves and having more tight estimate of populations. And secondly, well, it was the second bullet point here that even when the data exists, it is very difficult to process by hand. And in order to help people to be on time with the processing, well, we can propose data analysis that is better and faster. And this will be like the two parts of my talk. Feel free to interrupt me at any time. I'm not particularly disturbed by questions. So you can write them in the chat, you can raise your hand, and then hopefully Lauren will help me out with the questions. Okay, good. Part one. So we can help in better, smarter data collection. So by the way, if you want to know a little bit like the global idea of everything that I will talk about today and more, you can check out this paper we just published in Nature Communications. And it's basically an overview that is much broader of everything that I will be saying today, which will focus on drones and animal census in Namibia. Okay, so yeah, spoiler alert, drones and animal census in Namibia. So we have been running this project with our colleagues at the Kuziko Reserve, which is here in Namibia, so really not far from you guys. And basically in this, it's a private reserve, but where they really care about, you know, science and making things right, also in terms of automatization of the processes. And the first time when we started working together in 2014, so it's 8 years ago, basically, you know, they came to us and say like, hey, we would like to make this automatically, the whole discounting business, because it seems that we are very often either inaccurate with our measuring or after the poachers come. So, you know, we played European, unfortunately. We're like, yeah, no problem. We come with a drone, with an EB from SenseFly. In that case, we fly it over the reserve, and it's done. So it looks very simple back in the way, and of course, it will turn out not to be. You can imagine that. But at the end of the day, I mean, the idea looked a little bit like that. No, this is the Kuziko's Reserve in Namibia, and we thought, okay, let's buy a camera. It can be like a consumer, very cheap camera, because we want the system to be usable by anyone, and then mount it on a drone. So one of these foam drones that are very, very easy to replace. You can tape them if they break, because they also crash, and that's okay. And with this drone, with the camera, we can basically take pictures of the reserve and then count the animals. So it sounded extremely easy, but then we ended up flying the reserve in 2014, in 15. Now we've been doing that many, many times. And we go back with our drive, and the story is always the same. We have images like this one. So this one is from our very first campaign in 14. And then the story is to count the animals. So I don't know, if you ever want to play a game with me, can you tell me how many animals are in these pictures? And maybe you want to just to write a number in the chat so I can see it. Don't be shy. Even if it's wrong, I will not be mad. Ten, Idris. Thank you, Idris, for breaking the ice. It's very much appreciated. Okay, 10 is not bad. It's a good estimate. Anyone else has another idea? 7 from Lorraine. Yeah, 7, that's good. 5, 6. Okay, so I have the impression most people have been very busy looking at this part of the image, where we can see these 5 animals. I mean, it's very, very simple to spot them. They are, you know, on the sand. It's all right. 20, Emmanuel. Oh, we have seen this image before, right? So, okay, so it's not 20, but we're not far. So, you know, there are these animals here. Maybe those who say 8 or 9 have seen this, but it's actually a lot more. And many of these are very often, you know, at the border of the images. Sometimes they are resting under the trees, so they end up being in shadow areas, like in this case here. So in this specific image here, we have 17 animals. So, you know, we started for the idea that, oh, if we fly the drone, it's going to be super easy, but it's actually not always the case. It can turn out to be a pretty difficult task. And this is for a number of reasons. So one is that we just saw it. Now, the animals are relatively small. So we're talking about 30 by 18 pixels. So the pixels are on average 5 centimeters long, more or less. And there is not many of those. I mean, if you look at the entire footage of this first campaign, most of the images will not have any animals. So also, I mean, you can spend a lot of time just looking through images where there is absolutely nothing to see. And a third thing is that the animals are heterogeneous in appearance, of course. I mean, an impala will look very different from, I don't know, an elephant, but also the landscape looks very different. So what you're seeing here are images taken in the exact same campaign in Kuziko's, which is, you know, it's not like super huge. It's not Kruger Park. It's a small reserve, but still we can see a lot of diversity, both in terms of background and in terms of animal appearance. So, you know, the stripes, if you have a zebra versus an impala and so on. So actually the task turned out to be much more difficult than we thought. And that's okay, because, you know, we came back to Earth with a more realistic view on the thing, and we ended up accepting, you know, second stage of grief, no? So we accepted that the ranger alone will take days to spot all the animals on the images. So we needed to help out to automatize not only the data acquisition, but also the data processing. And so the first thing we needed, because we are a machine learning person, so we thought, okay, let's build a machine learning model. But to build a machine learning model, of course, we need some labels. So what we call a training set. No? It will be images with annotations of animals, which is exactly the exercise we did a second ago. For every image, we need to draw a box around the animals. So we teamed up with a number of colleagues. They were at the University of Zurich. That was me, actually, back in the day. There was ADR in Qatar, and Drone Adventure, which is the non-profit company that commercializes with, SenseFly non-profit. It's called Drone Adventures. And we ended up creating an app, basically, that runs on a phone or on a tablet, and where volunteers will basically receive images fairly zoomed in, and they will click on animals to basically create our labeling set. And this turned out to be an extremely successful exercise because people really wanted to play. So we had around 300 volunteers who basically in 2 days managed to go through the 26,000 footage of images we acquired in 2014 and spot the 1,000 animals that were running around in the National Reserve. And not only we had one annotation per image, but at least 5 persons watched the same image, which helped us to have not only a label of knowing if there is an animal or not, but also at the same time to have an estimate of confidence. So as you can see here, every red line here is one person who has been drawing. So some people just make a square, other people draw very closely, but in the end, these animals were like correct detections because they were detected by everyone, while these things on the right was detected only by one person. It actually ended up not being an animal. So it was also a way to, filter out all the things that were wrongly detected by one of our volunteers, because they were volunteers, so they were not experts, and they were driven by this envy of participating and helping in nature conservation, but not being an expert. Sometimes you also make mistakes. Even experts make mistakes. Yeah, don't get me wrong. Okay, so this was about data collection, and I'm not claiming that we are the only ones doing that, by far. So I just wanted to give you a couple more of these platforms that exist. These ones are way more advanced than ours, and they are still running worldwide. So you might have heard of iNaturalist or eBird, which are basically platforms where people take pictures of plants and animals with their phones and add the label, and it gets into an enormous database with a location. Or you have other initiatives like Wildbook, where they focus on one single species and they try to identify single individuals by mining social media and having communities of experts and so on. But long story short, you end up having these like big maps, in this case, worldwide from iNaturalist, of the different distribution of the different species. And then you can do a lot of learning from that to understand habitats and predation relationships, and hopefully the impact of climate change to the habitat of the different species. And don't get me wrong, it's not just data collection here. There is a lot of machine learning behind the scenes, because to be effective in these types of data collection, well, you need to be good at showing the right image at the right time. So, there is a lot of these active learning concepts. So meaning that if you have 1 million images you could show to a person, you don't want to do it randomly, because otherwise the person will just be looking at empty pictures for hours and then it will stop helping you. But if you use concepts of active learning, you can favor images where there is a higher chance to find an animals, or images that are more helpful for your model. And on the other side, if you do crowdsourcing, you can actually not forget about the crowd term in crowdsourcing. So you can start working on how to optimize your crowd and give a certain type of image to a certain type of user who will be more effective in resolving problems related to a specific type of images. Okay, I'll take a 2-second breaks here, and I will click on Q&A to see if there is an answer. So it was an answer to my game. Okay, so 12 is good. So if there are questions, just shoot. I'm very happy to take them, and I will take the 3 seconds to drink some water. But if you don't, you can also keep your questions for the end. It's fine, but I will feel less alone if there were some questions from the audience. Anyway, so again, feel free anytime. You don't have to do it now. Okay, so far we've been talking about data collection and how to make this data collection smart and useful and usable. But now that we have this this bunch of data that have annotations, and we want to do something about it. So you see here in this picture is a kind of an imagination of the different things that we can do when we have all this data about wildlife. So today we will talk basically about the pink squares below the zebras or the purple square below the bisons. But you can imagine a number of tasks. You can imagine pose estimation, so like modeling skeletons of animals, see how they move. You can do identification, so identify single animals, for example, based on the stripe of the zebra, or doing all kind of 3D modeling of the environment. This is also very interesting. And if you're interested by any of those, just check out the Nature paper. Today, I will talk only about detection. All right, so we were talking about flying the drone around with a camera and flying it over the animals. Sorry, there is an airplane landing, I think, just above me. If you hear strange noises, it's that. So once we have taken the images, the second step is to create the technology that is able to basically detect and count single animals. So in other terms, like creating these red boxes around the single animal in an automatic way. Because what we don't want to do is to be forced to have a person going through the whole footage by hand and verify that everything is correct or not. So this involves machine learning, and of course we were lucky enough that we had this labeling campaigns that I described before with the volunteers. So we had some images that we could use as an input, and we have these probability maps that were basically crafted by volunteers, and we could use these two elements to basically train a machine learning model that, given the images, will try to predict the map on the right. Okay, so I will unfortunately not have a million times to go through the details of the model. Imagine that is really something that learns a representation, so a number of filters, a number of variables that will basically be recombined many ways and end up being the map you are looking for. And so it might sound very simple and something that can be solved in no time, but it's actually a pretty difficult problem for all the reasons we have been discussing before. But the main one that was very tricky was that we do not have so many animals. So we want to train a model that is able to recognize animals, and we're basically giving more or less 1,000 animals in 654 large images. And when you chop them, they become these 26,000 images I was talking about before. And this is just for one campaign. Imagine we were repeating that every year. So the 25,000 just gets bigger and bigger. So in a way, we have a little bit more than 500,000 animal pixels, but we have several billions background pixels. So it's very difficult for a machine to learn what an animal looks like when we have so many confounding factors that can be, trucks, vegetation, rivers, logs, and you name it. So in this like first paper, when we started to look into deep learning models to learn animal appearance, we basically went through a number of different strategies to make a model able to learn when we are in this situation of very scarce labels and a large number of images. And this basically boiled down to 5 recommendations for training. You can find them in this paper in remote sensing on environment. If you are curious, just go on archive. It's open source. And basically, it was a number of things you could do. The first being model pre-training, which basically means that you don't train the model from zero with all these representation, these filters, these numbers initialized at random. But basically, we took a model from computer vision that was learned on 14 million natural images from the internet, and basically allowed us to learn geometric features. So the fact that, the back of the animal is a kind of a 30 degrees northwest southeast oriented color gradient, and this is something you also find in natural images. So why not using a model learned on natural images and then just specialize it to the problem of animal detection? Then we use other strategies. I'll just give you another, which is curriculum learning. And in this case, we were starting the learning of our model with just the images that contained at least one animal. In that case, we were making the task of our model much easier because the model knew that at every single image, there was at least one animal to found. So it had never to just predict an empty map. And then when the model was starting to be good at predicting the animal location, then we started to give also all the other images, so a much larger database, where the majority of images would be empty. And this will help the model better recognizing the different type of backgrounds. So you see different tricks that go over the training of a deep learning model. And by having all these models together, we basically managed to improve what was considered to be state-of-the-art before, which is the blue line here, that you see in a precision recall graph. So if you want the y-axis tell you how many false positives you are doing. So you want to be as high as possible. And the x-axis is how many of the animals we have found. So you want to be as close as possible to the one. So the best sector of this graphic is here, of course. But you see, the baseline will manage to detect all the animals, so all the 1,000 and something animals, but at the price of making 20,000 false predictions. While in our case, we were able to reduce this number of false predictions by a significant margin. So going at around 800 false predictions to detect all the animals in the dataset. Now, the good thing is that by continuing working on it, now we are more or less closer to something like that, which means that we are making very few misdetections but we still have to sacrifice a little bit of our recall. So we're not finding 90% of the animals anymore, but 85. It's a choice, and it's a choice that you can actually decide together with the rangers that are in charge of making this type of predictions. So this is the type of maps we were having with our first deep learning baseline, where all the animals are the green squares, so these are the actual animals, and the blue squares were the predictions of the deep learning models, while the red squares were the prediction of this baseline we had from previous research, which is in the end, let's be honest, predicting animals a little bit all over the place, but that's fine. The story is that this is a very powerful way of thinking because it's something that can scale very much, in the sense that you are reducing all this task of screening all the images you are capturing to the task of controlling whether a detection is correct or not. So you basically decrease the work of rangers or of volunteers, if you're doing that on the web, by a significant margin. And I wanted to give you an example, which is the one of the mega detector, which is a model created by Sarah Beer, who is a colleague at Caltech. And they have this model that, given tourist pictures or camera traps pictures of animals, I mean, tourist picture or camera traps pictures, they don't have to be of animals. They go into this model that will detect whether it's an animal, whether it's empty, if it's a human, or if there is a vehicle. And given this prediction, you know, the 90% of images that are empty, they go to the bin. You don't even have to screen them. Those where animals are detected, they can go to experts. They can do only the review of those and then be much more efficient in staying up to date with their camera trap footage. And if humans or vehicles are detected, then it can be used, for example, for anti-poaching efforts. So, you know, this is the type of accelerators through technology that can help the daily job of workers in national parks. And okay, I've been talking about detection, but there are many more things that we can do. For example, you could do tracking. So if you are flying with your drone, as you can see here, we're tracking a fox. And this is definitely something for which we have the technology ready to do something which is good. So the colleagues in Münster, they're now tracking ants, which is which is very fun, like to track the very small. And on the right side here, there are other colleagues in Milan, Silvia Zuffi, and they are working on 3D reconstructing the animals from videos. So you have a video, or in this case of the zebra, and you want to create a 3D, like a full 3D reconstruction, only having the image, which then allows you to, rotate the camera, seeing like the 3D shape of the zebra and so on, while also having a segmentation which is pretty accurate. So you see, I've been talking about detection, but there is much more that can be done. And definitely you see, then you can also track the fox and having the tracker. So it's actually very cool. Okay, let me go back to the chat. Oh, there is a question. So I'll stop a second for the question. So the question is, hi, how do you deal with double counting if the animal moves between the time of the photographs being taken? Okay, this is I get this question a lot. It's something that is very difficult to account for, because we're not doing individual identification, but we're just detecting animals as a bounding box around the animal. So you're right, if an animal is on 2 images, it's virtually impossible to make the difference. Now, the story is that with the drone, we tend to fly patterns that are, like shaped, I don't know if you can see me, but they are shaped like a serpent, no? So, okay, if it's in 2 images that are one after the other, meaning that the animal is running very fast in the direction of the drone, in that case, yeah, we could, with tracking, be able to discount for that. But if the drone is flying and then coming back and an animal is moved on the other, well, it will be counted twice. But even though this might sound like, oh, that's a pity, we're still way more accurate on what our colleagues had before we deployed the system. Because, going from sitting in a helicopter and trying to find the animal, come back home and scale the number up by the number of kilometers you have been flying, and something that is based on actual detection, even if you count the animals twice, some animals twice, you're still much more accurate. But, it's a fair criticism, and, I try to be very open about it. Thank you very much, Debbie, for the question. Cool. So let's see the Q&A. No, it's always the same. So good. Let's continue. So this is the last part. It's going to be very short because, of course, I am running out of time, more or less. And I wanted to, move out for a second from our latest deep learning model and how cool it is, and just showing how we can scale this up in a way that it becomes actually useful for multiple people in multiple reserves. Because, we have now our drone with the camera, it detects animals, but I'm pretty sure that many of you have noticed that my very wisely drawn little red squares on the animals are not super accurate, because on one hand, we have animals that are missing, like here in green, and there are predictions that are wrong, like here 1 tree was predicted as an animal, and here 2 logs as well. And so one thing that is important beside detecting itself is to really listen to what is important for ecologists and rangers. So on one hand, the ecologists we work with, they have a ton of mirroring campaigns, so they have a lot of images, and they want to basically having their detection, maybe the species out, or knowing if an animal is pregnant, if their head is tilted in a certain way, and they want to do it without not too much machine learning expertise, which also, raise the question on how accessible these models are for the people we want to help with this technology. And on the other side, we have the rangers, and the rangers want to keep monitoring their populations at a regular basis without doing a crowdsourcing campaign every time. So, they don't want their images to go on the web, because if you're trying to predict your rhinos from poachers and you put the images of the rhinos on the web, it's very simple to backtrack where the image was taken. I mean, once, just little parenthesis, something funny, I don't know, but so we had a press article about this study, and on Facebook there was a press release, and they put one of the images of our data set, and it was just the JPEG on the image was there in very bad quality, and the image was located up to a few kilometers accuracy, and I still don't know how they managed to do that. But I mean, this is the type of things that we should be a little bit careful when we work in conservation is not to give the person we don't want to have access to the information the access, just because we are doing everything in an open source and very crowdsourcing friendly way. Anyway, long story short, so we thought it was the time to make something that was useful at scale and that will, allow us to really reach a lot of people with this technology. So we created AID, which is our software suite for animal ecology. Then it was developed together with Microsoft AI for Earth, and we were in Wageningen University back in the day. And it's basically a software suite where anyone, so rangers, ecologists, you and me, when we have images taken from drones or even from the ground with your camera, you can, upload them. And there are a lot of deep learning models that are already pre-entered for you, so you don't have to do a single line of code to run in AID, which runs on the cloud. So we have virtual machines hosted on Microsoft Azure that basically process your images and detect whatever you want to detect. Of course, it's not free of labor. You still have to provide some examples of what you want to detect. For example, here a couple of these little squares, and then the model will give you all the other squares and show them back to you, and you will be able to improve them, and the model will retrain and improve, and by ping-ponging between you and the model, you will be as good as possible in solving your problem of animal detection. And it works at several levels, so you can go like image-based classification, like this will tell you giraffe. You can do point-based counting, so we'll just put a point. You can do bounding boxes, so precise boxes around the animals, or if you are into remote sensing, you could even do pixel classification. And there is a lot of deep learning models already pre-cooked for you, but you can upload your own if you like. I say that it was not labor-free, but it is free, like money-free, because it's 100% open source, so you can branch it, you can develop it with us, and you can use it free of charge. And I think this is the best part about AID, is that it will not cost you a single dime to run it. And it's being used. So we have our colleagues at Quest in Canada. They are interested in birds migrations, and they know that the birds tend to nest in this highland on the west coast of Africa. So they went there with their drones, take some footage, and then we used AID to decrease the annotation time from 3 weeks to 4.5 hours. So everybody was extremely happy of using AID for something practical, and not just for a paper, but actual for an actual conservation action. All right, I'm getting to the end of it. So just a couple of words to conclude. So I hope you have seen that conservation needs machine learning to speed up and scale up, and that as machine learning scientists we can do a lot to play our little part in the biodiversity crisis. And now the question is that, in the title I say machine learning helping conservation or helping machine learning. So basically, can we close this loop actually for real? So does machine learning need conservation? And I will say that for me, it's a definite yes, but it's something that is just starting. And I just wanted to put a couple of papers of people, not me, these are papers of someone else. And it's people who are trying to let percolate knowledge from ecology into the machine learning field. So for example, in this paper, the authors are trying to encode animal hierarchies, the genus, species, population type of things, and to use those in their loss function so that the prediction of the model will become consistent with the knowledge about speciation that we know from biology. We have this other work from Oisin Makadoha at ICCV 19, where they try to encode positional information, because we know that species tend to regroup at certain moment of the year in certain parts of the world. So we try to have a location encoder that, given the species, will let them spread more or less in space and in time. You see this Western honeybee that likes to be much spread in late spring, but in winter they tend to be very, very localized in specific areas with a favorable climate. And last but not least, again, biologists, ecologists know a lot about co-occurrence of species and predation networks, and why not using all this information that is known from ecology and put it into a deep learning model so that certain predation become more consistent with the ecological knowledge of the world. And this will make your maps less absurd in a way, because it will avoid that some species that are never found together to be co-predicted in space. And that's it, my friends. I hope you liked the 42 minutes talk I gave. I hope it was useful and interesting. Here in the pictures is the wonderful people I talk to every now and then, and who do wonderful research as well. You have seen some of their papers in this talk. And yeah, if you have some questions, please shoot. And yeah, it's a pleasure to be here. Thank you very much.
Devis, thank you very much for an excellent talk. And I'm pretty sure we will have lots of questions, and I will put again Lorraine on the spot to guide us through the Q&A session. So please either raise your hand or make use of the Q&A facility, and I will be very happy to give you the rights to ask your question in person. Yeah.
Okay, maybe I stop sharing my screen so we can see each other. Yeah, there we go.
I see that, sorry, Lorena, I don't want to take away your job. There are two questions of Debbie in the chat, Lorena.
Yes, but I think there is one you have already answered. So yes. I just going to tell the second one. So the question is, maybe for distinctive animals like zebra, which have unique strip pattern like a fingerprint, one could do individual identification to help reduce double counting if the animal moves.
Absolutely. I mean, that's a very good point. It still requires some thinking, because you need a lot of images of a single zebra to learn their specific patterns before you can identify them. So I mean, it's something you can do, I guess, in very like closed environment where we can monitor for a decently long time the same population. I think there has been a study published very recently in Nature Methods by Mackenzie Mattis, where they're like showing for bears that this works for bears. And I mean, the whole difficulty is that bears change a lot their fur during the year because of the hibernation patterns. But I mean, it's not my paper, so I'm not super proficient. And there was also a study from Tito Burkhardt about recognizing orangutans, but then they had really close up of their faces. Then they were using algorithms for basically face recognition to make the single animal identification. For the zebras, coming back the original question, there is the Zebra Rally, which is a computer vision exercise, let's say. I mean, I don't know if exercise is the right word, but they do it every year, and there are a lot of tourists going around in Kenya, if I remember well, and they take pictures of zebras, and then they deploy all these technologies for doing detection and identification. And at some point, they start to have enough critical mass of images of single animals to do the identification. So definitely possible, but it requires a little bit of, of labels at least.
We have a question of David Botta. So I think you can activate your micro and ask.
And camera. I'd like to see you.
Camera.
If possible, if you want.
Hi, Devis. I think the camera should come on shortly.
All right. Hello, David.
Anyways, so my question is I've got two questions. The first one, what was the optimal height of the drone that you found resulted in the best?
So in Kutikos, we were bound by legislation, so we could not fly lower than 100 meters. So we had to fly at that height. If you go much slower, you start scaring the animals. And you don't want to do that. So at 100 meters, we could have images at 4 centimeter resolution, which was more than enough. We tried to degrade that, so simulate if we were flying higher. And at 8 centimeters, it didn't change a lot. And at 12, the performance started to degrade a lot.
Okay,
So
that's a lot higher than I thought. Yeah. And
yeah, because they're noisy, especially if you go with a copter, you need to fly lower. That a good person to ask that is Blair Costello, who works a lot in Alpegeta, and she flies drones there since a long time, and they have been studying all this. So in case you want to check some papers from Blair.
Awesome, thanks, Devis. My second question, you showed us a large image of a few images that had been stitched together. I think it was the image where the two models had made predictions and you were comparing the predictions. That big image, did you make predictions on the smaller images and then stitch it together, or did you stitch it together to form the big image and then make the predictions?
We made the prediction on the small images.
Yeah. Okay.
Yes.
Yeah, and do you
also
think
because you're bound by the size of your GPU, and back in the days we didn't have much, so we had to keep it small.
Exactly, and I suppose because you've trained the model on the smaller images,
yeah,
if you now have to try and test it on a massive big image where the animals are
definitely like in object detection, this is a problem. If you were doing segmentation, that the size will not impact at all because you can predict larger images anyway.
Do you mind elaborating why, if you're doing segmentation, it wouldn't matter? Just trying to get my head around that.
Because you end up making a point-by-point segmentation at the end.
Okay.
So when you learn a semantic segmentation model, you learn at learning time you have a fixed side, which is the fixed window.
Yes.
But once the model is trained, you can do at inference time, you can do larger images basically.
Okay.
Because the weights will remain fixed.
I see. Awesome. Thank you so much, Devis. I appreciate it.
Yes.
Thank you for the question.
Yes, we have a question of Sean Venberg. So which neural network is mostly best for future use, ANN, CNN, or RNN?
It depends a lot on what you're doing. A CNN is good when you have image data because it's basically fit for that. So all the filters you learn are image-based in space. So if you're working on images like our images, well, you want neighborhood relationships to count, so you go with a CNN probably. A recurrent neural network, you have this concept of sequence. So recurrent nets are good if you have a time sequence, for example, because you will learn a model and then inject its output as an input. So this is something that we use a lot, for example, when we work on time series. So if you have a time series, a signal that goes in time, you use a model created for that. ANN, you can always use them. It's good for point estimations. So if your data are let's say points in a tabular environment where you have variables and every line is a different individual, then you can use an artificial neural network, but you don't have any concept of space unless you include variables that account for space. So the convolutional neural network, the CNN, is an ANN with spatial filters. And at the end, the last layer of a CNN in practice is an ANN because you do a fully connected. So you connect all, you lose the concept of space, like you remix all your variables into a single number. So it really depends on what you're doing.
And did you try the VNet or the UNet? It's my proper question too.
In this case here, we were using ResNet as an encoder. Was it a UNet as a? Let me think about it. So we were having only the encoder.
Mm-hmm.
So maybe I can put back the slides. So let's go back here and let's go back to the, where is it? Here. So you see, we were going to a ResNet 18 encoder, and the result was a 32 by 32 by 500 variables. So we were basically reducing the spatial component to 32 by 32. So it was basically only the encoding part of the unit. We were not going back to full resolution. So you can see our final prediction mask here. Can you see my screen, Lauren?
Yes, yes, we get.
So our final prediction was 32 by 32. So we were basically working in the space of the encoder. Since we didn't have a decoding part, it was not a unit. If you wanted a 500 by 500 prediction mask, then yes, we would do something like a unit.
Yeah, sure. We have a last question from Emmanuel Dufourc. Internally, we have spoke about using the idea of super resolution, super pixel methodologies to improve image quality from drones. Do you have ideas about this?
Oh, this is something that is very popular in satellite remote sensing. The question is always to get the ground truth at the higher resolution. So you should have to fly both heights to create your training set of images that are very high res and lower res. And then you can fly only the low res and predict the higher res image. The question would be, why don't you fly lower? But yeah, if there is an animal in the story, it makes sense because you don't want to scare the animal.
Yeah.
In the satellite business, it makes a lot of sense because you cannot change the height of flight of the satellite. So you basically take one satellite and try to super resolve the image of another sensor that is higher resolution. So yeah, I mean, there is a lot of algorithms around for that. So if you look in remote sensing literature, people went quite crazy with super resolution. So you can find a lot.
I think we have done with the question.
Okay. Yeah, then Lorraine, thank you very much for guiding us through the question session. And Devis, thank you so much for the really nice talk. You heard, at least I hope you got the feeling that there was real interest in what you're doing. And I hope that this colloquium helps us establish some connection between your group and the groups in South Africa that are interested in working on in a similar field. Yeah. So thank you very much, Devis, for your time and for preparing such a nice talk. And as I mentioned before, Devis agreed to meet us 10-15 minutes in our virtual Kumo space. I posted the link in the chat, but it should have opened up in your browser automatically according to Zoom rules. Yeah, and I hope to see most of you there just now in just a time to switch from Zoom to Kumo space. So Devis, again, thank you so much. I hope we will stay in touch. And if you happen to be in South Africa, please come and visit us, or otherwise we can make a plan to come and visit us directly. Yeah, that would be
with pleasure. Yeah, thank you very much for having me.
Thank you. Thank you very much, Devis, and thank you very much, Lorraine, for your time and for introducing Devis. Yeah. So thank you very much, everyone. Hope to see you in Kumo space just now. Thank you. The drinks are free in Kumo space, so please.
See you later.
Thank you. Thank you very much.
See you just now. Thank you very much. Bye.